Hello, my name is Angel Martinez.
My name is Marissa Bertuccio.
My name is Grant McConaughey.
My name is Ricky Picana.
Hello, my name is Derek Stone.
This is a presentation on the Marburg virus vaccine production process, and we are Group 6.
The Marburg virus is a virus that once it infects an individual will cause headaches, fevers, and even death. Within a total of 12 outbreaks, with only 2 of them managing to reach over 100 cases, one in 1998 and one in 2005, with both of them reaching a fatality rate of over 80%. This could be because there are no current vaccines or treatments available out in the market, although there are some currently in development. Our proposed solution is to create a solution of glycoprotein and VP40 in order to be used in vaccine development. We chose these two proteins because they are on the surface of the virus, which will hopefully aid in the attachment of antibodies, which will create an immune response of the body.
I'm going to be telling you about the overall process. So, development of a Marburg virus VLP on this scale would be unprecedented. The only studies that exist using this type of VLP were with guinea pigs and macaques. So, in order to get an idea of what the rate of production to base our process around should be, we took the amount used in these guinea pig studies and basically scaled up the mass by the ratio of mass of a human being to mass of a guinea pig to get an idea as to what mass of VLP we would be using for a human dose. We then multiplied this by the 54 BSL-4 labs that exist around the world that could potentially work with a Marburg VLP, and multiplied this by some additional considerations for number of participants in an experiment and experiments per year to get this value you see at the top of 24.3 kilograms per year, or 136 grams of VLP per batch. Our entire process was built around achieving these values. So because we knew what our final amounts should be, we were able to essentially work backwards, assuming reasonable losses at each of these steps, to ascertain what the conditions of our initial bioreactor should be. We did research on monode kinetics for yeasts and found these values for Ks, Umax, and Yxs. QP, basically the rate of production per yeast in an hour, was approximated using the mass of Marburg virus and the mass of a single yeast, and assuming a single yeast cell could make 10 copies of the Marburg VLP in 1 hour. From here, we were able to run a batch MATLAB simulation using monode kinetics, and we found that conditions of 1,000 liters of water, 20 kilograms of glucose, and half a kilogram of yeast were good for producing 190 grams of VLP at the end of the bioreactor process, which we had previously back calculated as approximately the amount we would need to achieve that downstream desired value of 136 grams of VLP per batch. How this would work is depicted in this process flow diagram. Essentially, sterilized media fills up the bioreactor, and then the bioreactor is inoculated with the yeast and the vector containing the virus-like particle gene. On the vector would also be a gene for excretion, which would make a lysis unit unnecessary. So the products from the bioreactor move to this centrifuge unit, where the supernatant moves on and most of the solids, the cells, are removed. Following this step, there are 2 ultrafiltration units. Because the Marburg VLP has a diameter of roughly 80 nanometers, the first ultrafiltration unit will have a filter diameter of roughly 85 nanometers and is designed to filter out everything larger than the Marburg VLP, whereas the second ultrafiltration unit would have a filter diameter of roughly 75 nanometers and would be designed to filter out everything smaller than the Marburg VLP. Following these steps, the process fluid moves to a size exclusion chromatography column, where the virus would elute in a certain step more than the other contaminants, which would be empirically determined. Following this, it moves to a final ultrafiltration unit, which is mostly to concentrate down the process fluid to a dosable amount.
These are the manufacturing costs for this process. They're all estimates, and the total is currently $1.9 million, and that includes operations, raw materials, utilities, maintenance, property taxes, and insurance. At this time, R&D, marketing, and administration are all very unpredictable costs, so they're not included in this total. But operations is the largest chunk of this total cost. About 7 operators are required per shift, and they each make $25 an hour. So that's about $1.6 million in and of itself. And then for raw materials, the chromatography resin is the most expensive, and then ammonia, which is the nitrogen source, glucose, the carbon source, and water for ejection account for a majority of the rest of the price. For utilities, this includes electricity, fuel, refrigeration, steam, wastewater, waste treatment, and cooling water. And then for maintenance, this was estimated as 4.2% of the total capital investment, and property taxes were estimated as 1.5% of capital investment. The estimated profitability of this endeavor is shown in this abbreviated cash flow sheet. All the values in the table are in millions of dollars, and then the net present value and the cumulative cash position are just in dollars. And this is based on a selling price of $206,000 per kilogram with a tax rate of 21%. And this is after 12 years, the estimated net present value is $99,604, and the cumulative cash position is $33,707. So overall, this endeavor is not very profitable, and this could be due to the fact that there are very few cases of Marburg virus, and the virus is quite expensive to make. This is a sensitivity analysis on the process, specifically on the net present value. The base net present value used here is $99,604 over those 12 years as calculated in the previous cash flow sheet. And we examined the sales price, the product concentration at the time of the harvest, the yeast growth rate in the bioreactor, any downstream processing losses, and then higher cost raw materials. And we used an increase or decrease of each of those costs or values by 10% for this analysis. So we found that sales price had the largest effect on the net present value with a range of about $56,000, positively or negatively. And then high cost materials also had a really large impact, and the other 3 factors had a much smaller impact on the net present value.
The regulatory requirements include approval from the Center for Biologic Evaluations and Research, otherwise known as CBER, and the entire process will be validated to ensure that the viral proteins that the process is made out of is at the required purity. It also involves an inspection of all equipment used and ensures that the mass balances from the machine are correct. So there has to be an evaluation of the vaccine's toxic and pharmacological effect through in vitro and in vivo animal testing before the product can be moved to consumers.
There are 4 uncertainties in our process that are worth noting. The first arose when we were calculating an annual production rate of our product. We had to base the amount of product per human dose off of a paper that only gave us an amount of VLP to dose a guinea pig. So we ended up scaling the number up by weight in order to find out how much to dose a human, which was a tad bit hand-wavy. Another uncertainty that we had in the process is the runtime of the bioreactor. Before putting the process in motion, we will need to find the optimal conditions to run our bioreactor at in order to get the most product. So we had to make an educated guess for the bioreactor runtime in order to get a final operating time for our process. We also made an educated guess for a downstream yield of our process because we don't have exact parameters of how much product exits the bioreactor. Finally, we are uncertain about when the next outbreak of Marburg virus will be. Although this doesn't directly affect our process, the uncertainty of the next outbreak of Marburg virus makes the construction of our process very important and urgent.
And these are our references. Thank you for watching.